Okay, good morning, all of you. Hello, everyone. Good morning, all of you. So we will start with a quote. So it is by John C. Maxwell. He says, "The better you are at surrounding yourself with people of high potential, the greater your chance of success." So that's why sometimes people call it depends on with what type of people you are living with. Okay, your life gets influenced with them. So sometimes people say you should have satsang, so that your thoughts process also will be like that. So it depends on their company. And many times people say, if you want to know about your son or somebody, so inquire about his friends. So naturally you will know what type of person he is. So always, if you are with people of high potential, and you also will try to have that much. Suppose if you want to do some exercise, or you want to go for walking, or you want to study with another person. If you study with another person who is of having high motivation and high caliber, naturally you also will try to have that qualities. Okay. And today is the birthday of Sanford Fleming. He is not Alexander Fleming, Sanford Fleming. And he is a Scottish surveyor and leading railway engineer who divided the world into time zones. Okay, you know that our world having different time zones. So he is the first person to do that. He emigrated at age 17 years to Quebec, Canada on 24th April 1845 as a surveyor. Later, he became one of the foremost railway engineers of his time. While in charge of the initial survey of the Canadian Pacific Railway, the first Canadian railway to span the continent, he realized the problems of coordinating such a long railway. When the railway is very long, so then he found some problems. This led him to the idea of time zones, which contribution to the adoption of the present system of time zones earned him the title of Father of Standard Time. And Fleming also designed the first Canadian postage stamp issued in 1851. It cost 3 pennies and depicted the beaver, now the national animal of Canada. So he is the Sanford Fleming, the innovator of the time zones. Okay, today we'll have just a review of thermodynamics. Okay, again, it is just through discussion and just like revision of whatever thermodynamics you know. Okay, we'll quickly discuss some of the things. And first, one thing I wanted to ask, what is the difference between, because usually people think that thermodynamics means thermo means heat and dynamics means movement. Okay, and so people always get confused with what thermodynamics deals with and what is heat transfer deals with. But actually, dynamics is not movement, it is work or the energy. So the science that deals with heat and energy is the thermodynamics. Okay, can you tell me what the difference of the subject that is dealt by thermodynamics and heat transfer?
Thermodynamics deals with the amount of heat and heat transfer. It it deals with the rate of the heat transfer, the rate of heat that
Yeah, actually, this
rate of
deals
heat
with
and
the
energy
amount of
transfer.
heat
Sorry.
transfer. Okay, the amount of heat transfer it is interesting. and this is interested in rate of heat transfer and mode of heat transfer. Okay, that is one of the main difference. Another important difference is thermodynamics deals with systems that are in equilibrium. Right? And this deals with systems that are not in equilibrium. Okay, so this is the main difference between thermodynamics and heat transfer. Okay, so the thermodynamics that we deal is what is called as classical thermodynamics, and this is also called as continuum thermodynamics. Sometimes we also call it as Newtonian thermodynamics. Sometimes we call it, thermodynamics is a part of mechanics, right? It comes like that. And so there are the basic assumptions are there, and many times we don't bother about that. And what are the actually why this is called as continuum is, so we assume that the system is continuum. This is very, very important. And okay, what do you mean by continuum?
Having no voids within the system.
Yeah. So it is something I'll tell you in a better way. Okay, if you actually density is defined as limit mass per volume, right? Delta by delta V, and delta V tends to 0, like this. Okay, V volume I'll write like this. Okay, so if I take volume here and density here, okay, and so suppose I take the room, okay, and if I find out what is the density of the air that is in the room, so I know the volume, I can find out the mass of the air that is there in the room, and I can find out some density like this. And if I can reduce the room to half, okay, what happens? What happens to density?
Remains
Remain constant.
Right, because it is independent of the. So what is it, intensive property or expensive property?
Intensive property.
intense
Yeah, so it is independent of mass. So here the density will be same as you reduce the volume. I reduce the size of the room, okay, half room, quarter room, 1/8 room, like that. I go on reducing it. So what happens is, as you go on reducing it, and when it becomes very, very small of molecular level, so then what happens is the number of molecules with the in the volume may change, because molecules will be going and coming and like that. So what happens is the density will be oscillating between two values like this. Okay, so this volume, I can take this as delta V. Okay, so if this is delta V star, so this is not delta V tends to 0, then it becomes infinite, right? So it should not be delta V tends to 0. It should be delta V tends to delta V star. So this delta V star is the limit which divides the continuum and non-continuum things. So here I can assume the system to be continuum. Here this is not continuum. Is it clear?
yes sir.
So that is the way actually this continues. So here, this side, if you want to deal with, this is microscopic approach, and this is macroscopic approach. So our thermodynamics is macroscopic. And if you want to deal with microscopic, we have to go to statistical, then
Statistics.
and which use kinetic theory of gases. Okay, and so actually there is a non-dimensional number called Knudsen number. Anybody knows what is the definition?
Mean free path by characteristic length.
Yeah, molecular mean free path by characteristic length. So if Kn is less than 0.01, then this is continuum. So as it increases, the characteristic length decrease, or molecular mean free path is more compared to characteristic length. So if it is some 0.1 to 10, then we go for what is called as statistical or kinetic theory of gases. If Kn is greater than 10, then we call this as free molecular flow. And we use what is called a rarefied gas dynamics or vacuum thermodynamics, like that. That is, if it is go outer space, right? In outer space, the Knudsen number is very large because molecular mean free path will be very, very large. There we go for rarefied gas dynamics. Or if you go to the vacuums, right? So the molecules again will be very, very far away from each other. Then we have to deal with this. So like that, I have limitations. So I have to assume it is continuum. And another thing is the Newton's laws must be valid. Okay, so Newton's laws must be valid. And what are the constraints? Newton's laws, though they are called as universal laws, there are some constraints about it. Anybody knows what are the constraints?
The reference frames.
Yeah, one is the frame of reference is inertial. Very good. Anything else?
So can't be applied in rarefied flows. So
Another thing, velocities
Is lessons
and velocity of light. Right? So if velocity is approximately velocity of light, then we have to use relativistic mechanics. Okay, relativity. And another thing, the mass should be finite. Right? So if mass tends to zero, like elementary particles and all, then we go for quantum mechanics. Okay, so these are further limitations. And another limitation, if you see, okay, what are the laws we say? First law of thermodynamics is conservation of
Energy.
energy. So we have seen continuity is conservation of mass, conservation of momentum, conservation of energy. Those things we have studied. But are they really true? Under what condition that is true? Is mass is conserved and energy is conserved? They are conserved only if there are no nuclear reactions. Am I right? If E equal to mc square, mass can be converted to energy and energy can be converted to mass. So you cannot say energy is conserved or mass is conserved. So actually, mass energy is conserved. Not mass alone or energy alone. Am I clear?
Yes, sir.
Yes, sir.
So the continuity or Navier-Stokes equations or energy equation all are valid only if there are no nuclear reactions. Is it clear? So there are so many assumptions we have made, but we just generally use thermodynamics, mechanics, and everything as everything are universal things. But there are so many assumptions we make to make those things work. So there are so many places where they won't work. Okay, this is one thing which we have to know, right? Okay, so these are the things first I wanted to stress on, and then quickly we will see what are these. We define what is system. System. What is system?
Anything under consideration.
So it is a quantity of matter on which we pay our attention, right? So what are the types of systems?
Open system,
The
closed system,
open, closed,
isolated system.
isolated.
Open, isolated. Okay, so closed means only energy transfer. So mass and energy transfer, and no mass or energy transfer. And okay, what is an example? What is ideal example for isolated system?
Universe.
Universe.
Yeah, universe. Okay, or practical thing if you want to take a perfectly insulated
Thermoflask.
mass flask. Okay, and closed system, open system, I think we need not discuss much about it. And another important thing is working substance. So there is one assumption we make for working substance. Anybody knows what is it? What type of substance we assume for thermodynamics?
So it does not undergo chemical changes.
What is that? We assume this to be pure substance. Okay, so what do you mean by this?
The chemically homogeneous.
Homogeneous and invariant in chemical composition. Okay, by assuming this to be pure substance, what is the advantage we get?
Properties are constant throughout the body.
But okay, not only that, that is one important thing. So this satisfies what is called as two property rule. Okay, sometimes we call it as state postulate also. Okay, and what do you mean by two property rule? The state of the substance can be
Can be expressed in independent parameters.
defined by any two independent properties. Okay, so here state, what do you mean by state?
Condition of a system.
Yeah, all the properties of the system. State is defined by properties. Properties are defined at a state. Okay, so what are all normal properties, thermodynamic properties we come across? Again, it is classified, right? So what is the classification?
Intensive, extensive.
Intensive, extensive, and sometimes they call it a specific. But specific is nothing but similar to intensive only. Okay, so what are the examples for intensive properties?
Pressure, temperature. Density.
Temperature, specific volume, density, specific internal energy, specific enthalpy, specific entropy. Okay, so these things come under here also specific. Extensive,
Mass.
Enthalpy, entropy,
internal energy,
volume.
energy, enthalpy, entropy, okay, volume, right? All these are extensive properties. Extensive properties per unit mass, we call it a specific, and this is also intensive. Okay, specific volume, specific enthalpy, specific entropy, they come under intensive also. Okay, and so the only thing that pure substance, it comes, okay, which is a pure substance? Is water a pure substance?
Yes, sir.
Yes. Steam,
Yes, sir.
ice,
Yes, sir.
air,
No, sir.
Dry air is moist air, not sir, but dry air is a pure substance.
dry air is a pure substance. Okay, air is a pure substance. And okay, then exhaust gases,
No, sir.
they are also pure substance only.
Pure substance.
Okay, and a mixture of water, steam, and ice,
Pure substance, sir.
Pure substance.
pure substance only, right? Then what is not pure substance? The one of the main example for pure substance is, okay, condensing air. Okay, if air
Humidity.
is condensed, right, then it is not pure substance, because the melting points or the condensing temperatures of different gases will be different. So at different temperatures, some of the gases in the air gets condensed and it will not be uniform composition. Okay, so like condensing air, so it is not pure substance, like that. Okay, anyhow, the important thing, okay, why we call it as independent properties? When change of phase is occurring, then pressure and temperature are
Constant. Dependent.
dependent properties. Okay, so normal way, when there is a single phase, then pressure and temperature defines the state of the substance. But when the change of phase is occurring, pressure and temperature are not sufficient, because pressure indicates temperature and temperature indicates pressure. So one more property is needed while change of phase is occurring. So that is another important point we have to remember. Okay, then we see what is equilibrium. So what do you mean by equilibrium? What are the types of equilibrium?
thermodynamic equilibrium, thermal equilibrium, mechanical,
Mechanical,
chemical equilibrium.
okay, and thermodynamic. So all of them together, we call it as thermodynamic equilibrium. Okay, so thermal equilibrium, when there is
temperature constant,
no dt, okay, or T is equal to constant. And mechanical,
force constant,
pressure constant actually. Okay, chemical, okay, composition constant. Okay, no chemical reaction. So actually, if there are no gradients of any thermodynamic property, then we call it as thermodynamic equilibrium. There should not be any gradient of any property. So if all the properties are uniform throughout the substance, then we call it as equilibrium. Okay, and because the state is defined by two properties, Okay, so a thermodynamic chart is drawn between any two properties. Okay, so suppose maybe pressure and temperature. And so any point on the chart is a state, right? So any point on thermodynamic chart defines the state of the substance. Because this gives pressure and temperature, and other properties can be calculated from this pressure and temperature. Okay, and if you see the PVT diagrams, okay, this suppose I draw PVT diagram of a substance. So how will be this? You will see only 3 lines. Am I right? For any substance, if you draw the PVT diagram, in all the phases, if you want to show, right, it comes something like this. Okay, like this. And so this is vapor state. Okay, this is liquid state. This is solid state. And this point is called as, what is this?
Triple point.
Critical point.
Critical point. And this point is
Triple point.
triple point. And this line is
Solid sublimation.
sublimation line. And this is
Vaporous line.
vaporization. If you are going through like this, vaporization. If you are coming like this, condensation. Okay. In the same way, if you are going like this,
Melting.
melting line. And if you are going like this,
Solidify.
solidification. And if you are going like this, that is sublimation line. If you are going like this, anybody?
Precipitation.
Yeah, very good. Precipitation. Right? So like this. And there is one particular thing. All PT diagrams will not be like this. There are 1 or 2 exceptions. Anybody knows like that?
Water, bismuth.
Yeah, water. How will it be?
Solid to liquid line, it will be concave.
Yeah, very good. That's right. So this is for other than water. So which these are substances which contract on freezing. Right? And what happens to water during freezing?
It depends, sir, up to 4 degrees.
Expands on freezing. Okay, water expands on freezing. This is a very peculiar property it has, right? So it will be something like this. This is critical point. Like this. Okay, so all these things, if you see these lines, as pressure increases, the corresponding saturation temperature increase, or saturation temperature increase, pressure increase. Saturation pressure and temperature, they are proportional to each other. Only for water, right, the solidification line, this is having negative slope. This is positive slope, this is positive slope, and in the previous figure, all having positive slope only. Right? But for water, the solidification line or melting line has negative slope. So if pressure increase, saturation temperature decrease. Okay. And if pressure decrease, saturation temperature increase. Okay. That is a peculiar thing for water. Water expands on freezing. Okay. And one interesting thing I will tell you here. Okay, there is one particular statement that a substance can be evaporated any number of times without going through condensation. So this is a particular interesting statement. So somebody says you can evaporate a particular substance and again evaporate it and again evaporate it without going through condensation. So first, initially, you may not be able to understand what is this without condensing, how can you get it again evaporated? Okay, so here, if you see this particular critical point, that is interesting. Okay, suppose if I take a substance at this particular state and at constant pressure, I heat it, constant pressure heat addition, right? So what happens? It goes like this. When it is going like this is sensible heat addition. Whenever it crosses the line, there will be latent heat addition. Okay, so here there will be evaporation taking place at this point. And once it crosses, there will be complete vaporized state. Am I clear?
Yes, sir.
Yes, sir.
Now, isothermally, I increase the pressure. So up to some point here. Is there any change of phase? Unless it crosses a line, there will not be any change of phase you will observe. Am I right?
Yes, sir.
So it will be vapor state only. So what happens is when you are cooling it under constant pressure like this, if you are coming in this way, now also it is not crossing any line and you will not see any change of phase. And now if you close this and if you come back in this way and come to the original state, you will not see any change. You will not see any condensation. But if you see that it's a liquid phase, but you will not see the condensation. But if I go again like this, again, it crosses the vaporization line and there will be evaporation takes place. And so if you go on in this cycle, you evaporate it any number of times without going through condensation. Am I clear? So it looks paradoxical, but it happens. You will see the boiling. You can see the bubbling when it is evaporation taking place. And then in all the other three processes, you will not see anything. And again, it starts boiling here. Am I clear about it?
Yes, sir.
Yes, sir.
Okay. So this is something interesting. Actually, if I can say something like this. Actually, in Visakhapatnam, there is a King George Hospital, KGH. Okay, people who are in Andhra Pradesh, they will know about it. So it is on a hill. It is constructed on a hill. And what happened when I am a child, I went there and I went to OP. So from the road, I gone into the OP. And they told me to undergo some tests. Okay, so then I took those medical things and I went to lab. So they told it is on the upstairs. And then I went on to the staircase and then I got my testing done. And they asked me to buy some medicines. And I came out and again I came to the road. Actually, I am in the first floor, but when I came out, I am on the road. Am I clear? Actually, there is a slope of road slope is there. Here, the ground floor is there. And here there is first floor. And I got into the ground floor. I went on the staircase and I came out. I got the road again. I nearly didn't understand how I got the road again. I am on the first floor. Am I clear?
Yes, sir. Yes,
So
sir.
I can climb the staircase any number of times without coming down the staircase. I enter the OP, I climb the staircase, I come out and I come by road. Okay, there is no stairs there. So like that, it is something of that sort. Okay. leave that. So we will go to
So, sir, when the vapor converts to the liquid state,
yeah.
so can't we mark a line at that point?
No, we don't know when it is converted to water.
So can't you see that?
We can't see that. That's what is interesting.
Oh, okay, sir.
We will not see the change of phase, like getting condensed or something like that. But when you come here, it will be in the liquid state. When it is changed, we cannot clearly observe.
Oh, okay,
Okay.
sir. Yes, sir.
Yeah. Okay. Then coming to the laws of thermodynamics. Okay. Actually, first they came first law, second law, and third law, and they thought there will be a fundamental law they have missed, and that's why they named it as zeroth law. Okay, what does it say?
If two words,
Sir, if three systems, namely A, B, C, are thermal equilibrium with each other, means if A is thermal equilibrium with B and A is thermal equilibrium with C, then
B
both
and C
B
are
and
in thermal
C.
equilibrium. Okay. If two bodies are in thermal equilibrium with a third body, these two bodies are in thermal equilibrium. Okay, that's what zeroth law says. And this is used in science of
Thermometer, sir.
thermometry. That is for temperature measurement. Okay, we take some substance like ice or water or something, then we are standardizing the thermometer with that. And whenever the thermometer is in equilibrium with some other body at that particular point, then we say that also has the same temperature. Okay, so in science of thermometry or for temperature measurement, we use the zeroth law. And then we have to talk, before that, we have to talk about energy. Okay, so internal energy, heat, work, all these are energies only. And these two are energies in transit or energies in movement. And internal energy is just stored energy. That is the main difference between internal energy and other forms of energy like heat and work. And so internal energy, it is sensible energy, latent energy, and nuclear energy. So all these energies together. And what do you mean by sensible energy? It is due to molecular movement, like translation, rotation, vibration, spin of molecules. Okay, so all these are responsible for sensible energy. And all these energies together, we call it as internal energy. Okay. And coming to heat and work, and both are identified or recognized at the boundary only. Okay, so what do you mean by boundary? This is system, this is surroundings, and this is boundary. This is closed system, and open system we call it as control volume. This is control surface, and this is surroundings. Okay, this is control surface or the boundary. And so heat and work are recognized only in the boundary, and only when transferred. Okay, when this way or this way takes place, then only when it crosses the boundary only, we identify heat and work. Okay, both are transient phenomena, and boundary phenomena. Okay, so that is important. Okay, what is the difference then? How can you identify whether it is heat or work? When energy is transferred or crossing the boundary, how to identify whether it is heat energy or work energy?
Sir, if
The
energy
energy
is
transfer.
transferring due to temperature, then it is heat.
That is the main difference, right?
Yes.
Heat transfer is only due to temperature gradient. And the energy transfer due to any other reason is work. Okay, that is the main difference between heat and work. Okay, if it is due to temperature gradient, it is heat. Okay, and another important thing, there can be heat transfer. Can there be heat transfer without temperature gradient? Can there be heat transfer without temperature gradient?
No, sir.
Yes, sir.
How?
Radiation.
Phase
When
change is changing.
During change of phase. Right? When it is heated, right? Heat transfer is taking place, but during phase changing, its temperature will not change. So there can be heat transfer without temperature gradient.
Sir, but the temperature gradient is not within the system, sir, but it will be temperature gradient with the system and surroundings, sir.
Yeah, maybe outside temperature is same, inside temperature is also same.
Then there won't be any heat transfer. Right, sir?
Okay, maybe temperature rise, I can say. Okay,
Yes.
right?
Energy content will increase, but temperature will not.
Remains constant. There can be
Okay.
heat transfer, but temperature may remain constant. Okay, and can there be temperature rise without heat transfer?
Yes, sir. If we compress,
Yeah, work transfer also can increase the temperature. That is, if I put a paddle wheel and if I churn the water, its temperature rises, right? So there can be temperature rise without heat transfer, and temperature may be constant even there is heat transfer. Am I clear about it?
Yes, sir.
yes, sir.
Yeah. Okay, then we come to first law. So what is the first law?
The conservation of energy.
Okay, can you give me statement?
When a system is undergoing a cycle, then the change in the heat transfer equal to the work transfer.
Yeah, very good. Actually, when a closed system undergoing a cyclic process, then the cyclical integral of or the net heat transfer is equal to the net work transfer. And previously, when I talked about heat and work, okay, there is one more thing. Both are path functions, and both are inexact differentials. That is, I cannot write dq or dw I cannot write like this. I have to write delta Q or delta W. Okay. And if it is a property, properties are point functions. And they are exact differentials. Means dp, dt, dv, like that I write. That is, if it is undergoing a process from 1 to 2, dp will be equal to p2 minus p1. Similarly, 1 to 2, dt is equal to t2 minus t1. But integral 1 to t, 1 to 2, delta w is not equal to w2 minus w1. This is equal to w12 or 1w2, like that. Okay, because it's not a property, I cannot say this much is work at the point state 1 or this much work is a state 2, like that, because it's not a property of the system. So these are path functions, and properties are point functions. Okay, so this we'll write it as like this. And also I can write this as delta Q minus delta W equal to 0. Okay, this is for a closed system undergoing a cycle. And if I want to apply it to a process, then this is delta Q minus delta W becomes equal to change in energy of the system. I think you know the just a proof like this. If it is coming from state 1 to state 2, like this, and again if it is going back to this, and this is a cycle, and this is a process A and this is process B, and so integral 1A to delta Q minus delta W plus integral 2A1 to B1 delta Q minus delta W equal to 0. Okay, for the cycle, this total is equal to 0. And if it comes by another process C like this, and if I consider 1A to C1, so integral 1A to delta Q minus delta W plus integral 2C1 delta Q minus delta W equal to 0. So from these two, because these two are same, these two must be same. So integral delta Q minus delta W to B1 is equal to integral delta Q minus delta W to C1. Means delta Q minus delta W is independent of the path. Whether it is come by B or C, so this change is equal to, it can be written as change of some property of the system, dE. And because it is a closed system, the total energy is nothing but only internal energy of the system. So delta Q minus delta W is equal to dU. So this is the first law applied when it to a process. And U is called the internal energy or mu property for the system, comes through first law of thermodynamics. Okay, that's what it says. So delta Q minus delta W is equal to dU. Like this. Or delta Q is equal to dU plus delta W. And coming to the thermodynamic chart, right, if I have PV, right, so and this is isobar, and this is isocore. Okay, just like that. Okay, so isobar is P is equal to constant. So if PV equal to RP, okay, and the general process equation, if you write it as PV power n equal to constant. Okay, so sorry. So here for isobar n equal to 0, and for isocore n equal to infinity, and isotherm P equal to constant or PV equal to constant. So it is a rectangular hyperbola where n equal to 1. This is isotherm, and because this is 0 and this is 1, so if it is some 0.8 or something like that, it will come here. If it is 1.4 or something like that, it will come here. So for adiabatic, n equal to gamma, which is equal to 1.4. So this will be adiabatic line. Okay. So adiabatic is more steep than isotherm.
Sir, all these processes should be reversible.
Yes,
All these processes should be reversible.
all these processes.
Should be reversible.
No, these processes, they are quasi-static process. This is yeah, actually I want to tell about this. So what do we mean by quasi-static process?
PV raised to power n differentiated from isentropic process.
Infinitesimally small.
Infinitely very small process for
So
for this process
Small deviation.
intermediate.
at any state, the deviation from equilibrium is infinitesimal. So it should be a very slow process. And if it is not quasi-static, it cannot be drawn as continuous line. Okay. Now somebody is asking reversible process. Okay, what do we mean by reversible process? What do we mean by reversible process?
Quasi-static without friction.
Retracting the same process without any losses.
When it can come back to initial state. Here important thing, without leaving any
effect on surrounding.
environment or surroundings. This is very important. Anything can come back, okay? When it goes like that, you can always come back to the original state, but it should not leave anything in any change in the environment. Okay, if you come to my room and go away, there should not be any change. I should not notice that you have come and gone. But if you come here, maybe your scent comes here, or your footsteps come here, or some change, if it occurs, I can notice that you have come and gone. Okay, some state change, it happens here, right? So even your breath may change something here, and I may notice. So there is some trace of it is left in the surroundings. It should not be there. Okay, now what are the causes of irreversibility?
Sir,
Yeah. And
Sir,
our
PV
static process, is it reversible?
So it will
Sir,
be
PV
reversible if friction will not be available.
Suppose if you have Otto cycle, okay, you tell me what are all the processes? Are they quasi-static process or reversible process, or what are they? Otto cycle, you have two constant volume process, two isentropic processes.
Sir, original Otto cycle is not a reversible process, sir. If we take air standard, it will be
Ideal Otto cycle I'm taking. Ideal Otto cycle.
Yes, ideal Otto cycle is reversible.
So only internal reversible, sir, not externally.
Yeah, that is important. It is not a reversible cycle. If it is a reversible cycle, it should be equal. The efficiency should be equal to Carnot cycle. Am I right?
Yes, sir.
These are all quasi-static processes. They are not reversible processes. Isentropic process is reversible. Constant volume and constant pressure process are not reversible. They are quasi-static processes. Okay, so remember, all reversible, this is important. All reversible processes are quasi-static. Because I have drawn continuous line, right? It is a quasi-static. But all quasi-static processes are not reversible. Am I clear?
Yes, sir.
Yes, sir.
So this is very, very important. Many people think that all these processes are reversible, or reversible process can be drawn as a line. No, no, no. Quasi-static process only can be drawn as a line. But some of the quasi-static process can be reversible process, but all not quasi-static are not reversible. Okay. So only two types of processes are reversible. So adiabatic process without friction, okay, which is isentropic. This is reversible. That's why reversible adiabatic is also called as isentropic process, right? And the other one is isothermal heat transfer with infinitesimal temperature difference. Okay, this is important. If there is a finite temperature difference and if there is heat transfer, that is not reversible because it can go from high temperature to low temperature. But the temperature difference is infinitesimal, then the heat transfer is reversible, considered to be reversible. Okay, that's why if you see Carnot cycle, which will have two isentropics and two isothermals, but these isothermal process must be considered the temperature difference is very small during the temperature heat transfer, then only this Carnot cycle works. That's why Carnot cycle is not practical. Okay, why? Because temperature difference, if you want to have infinitesimal and if you want to have some heat transfer, it takes infinitely long time. Am I clear?
Yes, sir.
Reversible isothermal heat transfer, it takes very long time. So if you want to have a quick cycle, you cannot have that, right? And similarly, compression and expansion
Very fast processes.
without heat transfer should be very fast enough. Then only I will not have this friction will be negligible and reversible isentropic process will happen. So you cannot have a cycle with such a fast process and such a slow process. So that's why Carnot cycle is not practical. Okay.
And also work done will be very less.
Pardon? Yeah, work will be very less because actually if you draw the Carnot cycle, it comes like this, comes like this, comes like this. And this area is very, very small. Okay, the work will be very, very small. Okay, if you want to have work, you have to have sufficiently long time or something. Okay, so that is the causes of irreversibility. There is what is called as internal irreversibilities and external irreversibilities. So internal irreversibilities are due to the friction, solid friction, liquid friction. Okay, or turbulence or mixing. So all these are internal irreversibilities. External irreversibilities is like heat transfer with finite delta T. This is external irreversibility. Okay, within the system, if the irreversibilities are there due to friction, turbulence, mixing, all, they are called internal irreversibilities. And if it is during work transfer or heat transfer, if there is a finite gradient, then you cannot reverse it. Okay, so that is external irreversibility. So these are important things. Okay, then actually if you apply this delta Q is equal to du plus delta W. And okay, the one more thing I forgot, the work transfer delta W is nothing but PdV. Okay, this is for a simple compressible system. Okay, simple compressible system, delta W is equal to PdV. So delta Q is equal to du plus PdV. This is for a closed system. Okay, so when you apply this for a open system, first law for open system, then delta Q is equal to this. This is actually change in total energy, but we have not used d of Ke and d of Pe because it is a closed system. And here I have to use du plus d of Ke plus d of Pe plus delta W. And in addition to this, because it is a flow system, there is something entering and something is leaving. There is what is called as flow work. And this flow work is PV. So D of PV, this additional thing will come here for a open system. Okay, so we defined U plus PV is equal to H. So I'll write this as DH plus D of KE plus D of PE plus delta W. This is for open system. In a simple way, I told in a simple way.
So
But
potential energy can be taken for closed system. Why sir we are not taking potential energy for closed system?
no, here there is nothing crossing. Okay, potential energy is within the system only, right?
Okay, sir.
That's right. Okay, and if you want to write a generalized first law for a flow system, so this is if you know, that is better. And if I have different inlets and different exits like this, and this is called as total energy of the system, right? So the rate of change of energy of the system, right? This is a rate equation. And if there is equal to, if there is heat transfer into the system, okay, so there will be increase in the energy, so Q dot. And if it is work done by the system, so there will be decrease of the energy, so W dot. And some things are entering, right? So m dot, it increases the energy, so m dot I into Hi plus Ci square by 2 plus Gzi. And some things are leaving, exit, so it is reducing the energy. Okay, this is the generalized rate equation for any open system. Okay, it can be unsteady flow or uniform flow or whatever it is. If it is steady flow, then d is change of energy of the system is 0. dECV by dt is 0. And mass flow entering will be equal to mass flow leaving. It will be like this. So it will become Q dot minus W dot plus M dot into HI minus HE plus CE square minus CI square by 2 plus G ZD minus ZL. Or if you write in the previous way, Q dot is equal to, I take to the other sides, M dot into HE minus HI plus CE square minus CI square by 2 plus G into ZE minus ZL plus W dot. Okay, so this is the way I have written in the previous thing. So this one, dH plus d of kinetic energy, d of potential energy. And so this is the generalized flow equation. Okay, I think we'll stop. We'll continue and yes.
Sir, I have doubt. Sir, in PV raised to power n is equal to constant relation. So, what are the conditions required? Like, it should be adiabatic and it should be reversible or not?
Pardon, just repeat.
Sir, in PV raised to power n constant relation.
Yeah.
So, it is required to be a reversible process or not? Sir?
Okay. If it need not be necessary. Okay, it's not. It can be adiabatic only. It need not be reversible adiabatic.
And sir, in we can say in D, if the work done is equal to PdV, so here is also the
I will come
reversibility
to that
required.
just 1 minute. Okay. So here delta Q is equal to du plus delta W, right? And adiabatic means delta Q equal to 0, right? And so du plus PdV is equal to 0, and du is equal to CB dt, right? And PdV dt by gamma minus 1, right? And PV equal to RT, PdV plus VdP is equal to RdT. So PdV can be written as RdT minus VdP, right?
Yes.
Equal to 0. And actually, if you simplify this, you are going to get PV power gamma, sorry, PV power gamma equal to constant. I didn't assume any reversible anything.
Yes.
Am I clear
Sir,
about it?
if we write dW is equal to PdV, then it should not necessary that the process should be reversible.
No, it need not be reversible. It is quasi-static. That is delta Q is equal to TdS for reversible, but delta W is equal to PdV for quasi-static. Because this is used for isobaric process, isochoric process, isothermal process, all processes delta W is equal to PdV only I have used, right? It
I
need
think
not be
it should be
reversible.
for the
Delta
conditions should
W
be
is
like
equal to PdV is for a quasi-static process only. It need not be reversible process. Okay?
I think it is valid for closed system only.
Yeah, close the system.
Okay, sir.
Okay. Anyway, just think about it. We will discuss in the next class. Okay. If you have any doubt. So next class we will one class I will spend on entropy and reversibility, some things like that. Okay. So I will see whether I will spend that on that or I will continue this gas turbine cycle. Okay. So whichever you are interested in, if you want, we will spend some time on thermodynamics or we will Okay. We'll have the story then. I think the time is getting over long back. Anyhow, I think you have some more time. 10 o'clock, till 10 o'clock, I think you are free. And okay, we'll have the story. So it is a story, A Carrot and Coffee Beans. A young woman struggling with life went to her mother and told her how her life was miserable and hard for her. She was tired of fighting and struggling with her problems and wanted to give up. Okay, she got depressed. She got lost all the confidence and hope and all. And then her mother, without saying much, took the young lady to the kitchen. She filled 3 pots of water. In the first pot, she placed carrots. In the second pot, she placed eggs. And in the last one, she placed some ground coffee beans. And she let them sit and boil without saying a word to her daughter. The daughter wondered what her mother was trying to do while she was complaining about her life. And after some time, the mother turned down the burner, fished the carrots and the eggs out, and placed them in a bowl. Then she ladled the coffee out into a cup and turned to her daughter and she asked, "Dear, tell me, what do you see?" "A carrot, egg, and coffee," she replied. "Look closer and feel the carrots." The daughter noted that they are very soft. The mother asked her to take an egg and break it. The interior of the egg was hard boiled. And finally, she asked her to sip the coffee. Its rich aroma brought a smile to her face. Okay, then the daughter asked, "What does all this mean, mother?" All the 3 items, carrot, egg, and coffee, went through the same situation, the boiling water. However, each reacted differently. The carrot was initially starched, hard, and unrelenting, and however, after being subjected to boiling water, it is softened and became weak. The egg was fragile and thin outer shell, with a thin outer shell and its liquid interior. But after being the boiled water, it is hardened in the interior. Initially, it is liquid-like thing and it is hardened. And the ground coffee beans were unique. As it came to the boiling water, it changed the water and gave its incredible aroma. "What are you?" she asked the daughter. "How do you respond in difficult situations? Are you a carrot, an egg, or a coffee bean? Are you a carrot that seems strong at first but becomes soft and loses its strength in adversity? Are you an egg that starts with a malleable heart but hardens with the heat? Did you have a fluid spirit, but as you struggled with problems, have you become hardened and stiff? Did the problem harden your free spirit? Or are you like coffee beans, the beans that change the hot water, the adversity, into an aromatic drink? If you are like the coffee beans, when things are at their worst, you will get better and change the situation around you. When the hours are the darkest and trials are the greatest, do you elevate to the next level? Life is full of ups and downs. But the only thing that truly matters is how we choose to react to situations around us and what we make out of it. Life is all about learning, adapting, and converting all the struggles into something positive. When it rains, it pours. Maybe the art of life is to convert tough times to great experiences. We can choose hate the rain or dance in it. It is left to you. It's not what happens, but your reaction to it that matters. Okay, thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. See you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you,